Okay, thank you for the introduction. I'm going to talk to you guys today a little bit about some of the most recent work we've done in developing a non-invasive method to diagnose skin cancer using multimodal spectroscopy. So just kind of start off, everybody's familiar with skin cancer, and it's known to be a public health issue. It's a public health issue. It's also the most common form of cancer in the United States now, according to the Center for Disease Control. There are roughly 5 million skin cancers that are diagnosed annually. These span melanomas, you see here on the left, as well as the non-melanoma skin cancers, basal cell carcinomas and squamous cell carcinoma. The current methods to diagnose skin cancer involve a visual inspection by a dermatologist, who then decides whether or not to biopsy the lesion, and finally sending this biopsy lesion off to the histopathology lab for analysis. Here's an image of a typical slide that the histopathology lab will look at. There are, however, some drawbacks to the current methods of diagnosis. The first is that the biopsy itself is, although it is an outpatient procedure, it is a bit invasive, since it does involve a minor surgical procedure. The decision to biopsy is also made by the dermatologist, and based on their experience as well as their visual perception of the lesion. And as such, not all biopsies are necessary or may actually be necessary. And so this is sort of an important issue when there are 8 million biopsies that are performed per year. In addition, there is a very high cost to patients and the healthcare system. With this many biopsies, we estimate it's roughly about $2.8 billion spent per year in doing biopsies. And so there is a critical need, a demonstrated need for a non-invasive method to diagnose skin cancer. So as everybody knows, skin is pretty well suited for non-invasive optical interrogation, since it's very easy to access. And optical spectroscopy is one way to do this, and this can give you morphological and biophysical information about the tissue, and as well as being a non-invasive method. So our group utilizes a multimodal optical spectroscopy, so a few different forms of optical spectroscopy. And what we aim to do is to use multimodal optical spectroscopy to give what we call a spectral biopsy of a suspicious lesion. So our spectral biopsy approach combines 3 forms of optical spectroscopy. The first is diffuse reflectance spectroscopy, which I'll refer to as DRS, fluorescence spectroscopy, which I'll refer to as FS, and Raman spectroscopy, RS. So all the light is delivered, and all spectra is collected through a single 3-in-1 fiber optic probe, and all the collected spectra is analyzed with computational models to provide an end goal of a diagnosis of the lesion. So our group has previously shown that this approach is promising. And some of my predecessors in the lab have initiated a clinical study to assess the spectral biopsy approach. It showed that malignant melanoma was able to be classified from benign pigmented lesions with very high sensitivity and specificity. Non-melanoma skin cancers were also able to be classified from precancerous lesions, also with very high sensitivity and specificity. And so this clinical study showed that accurate diagnosis requires a combination of multiple optical modalities. So our current spectral biopsy system has a 3-in-1 fiber optic probe, as I mentioned, as well as various light sources and detectors for exciting and collecting the different forms of spectroscopy. So for DRS, we use a xenon flash lamp. For FS, a 337 nanometer nitrogen laser, and for Raman, an 830 nanometer diode laser. And the spectra is collected by a UV visible spectrograph and CCD camera for DRS and FS, as well as a Raman spectrograph and CCD camera for Raman spectroscopy. There are, however, some limitations with our current system. The first is that, I don't know if it's easy to tell in this picture here, but it's actually a pretty large system, and as a result, it's hard to transport to and from the lab and to the clinic, as well as move around in the clinic. The instrumentation used in the system is pretty high-end and research grade, and so as a result, it's quite expensive. And finally, the custom fiber probe we have is has a specific design that's a little bit difficult to manufacture, so that's also rather expensive. And so with these issues in mind, we wanted to try and design a more clinic-friendly system. So our next generation spectral biopsy system, again, we'll use a 3-in-1 fiber optic probe. So kind of to discuss briefly what's in the current system. This current probe has 7 fibers for collecting Raman spectroscopy, as you can see here. And what's special about this probe design is that there is actually a somewhere around probably 500 or 600 microns, less than 1 millimeter hole drilled in front of this front lens for diffuse reflectance and fluorescence spectroscopy collection. So this hole, because it's very small, is very difficult to drill. So this probe is a little bit hard to make as a result. So our proposed new probe design, we'll have a few less fibers for Raman detection, but also no hole drilled in this front lens. So this is an important consideration in being able to manufacture and possibly mass produce this probe. In addition, we've also looked at using a few different light sources and detectors for this next generation system. For diffuse reflectance and fluorescence spectroscopies, we're intending to move to a multi-wavelength LED light source that will provide excitation light for both methods of spectroscopy, as well as again, another 830 nanometer diode laser, but with a higher power output for Raman. The detectors that we're intending to use for this new system are small form factor spectrometers, both for diffuse reflectance and fluorescence, as well as a small form factor spectrometer for Raman collection. So you can see all these different components labeled here in the box. And all of the components will be computer controlled in LabVIEW with a synchronized acquisition and data collection. So to characterize our new system, we first wanted to look at these new components and, as part of this, compare our current and proposed new probe designs. And as part of these characterization experiments, we performed some experiments both in vitro and in vivo. So in vitro, I'll show you some of this in the next slides coming up. We looked at reflective standards as well as tissue simulating liquid phantoms for diffuse reflectance spectroscopy. Fluorescence standards for fluorescence, and a Raman standard, namely naphthalene, to characterize the performance of our new components. And we also took some in vivo measurements using all 3 spectroscopy methods on human skin. So this first set of results here is for the diffuse reflectance spectroscopy data collection. So these are measurements taken on reflectance standards. So on the left here is data from the current probe. On the right is the data from the new probe. You'll see this trend in the next slides. So these are measurements taken on calibrated reflectance standards with a relatively flat spectral profile. So as you can see, measurements from both probes are in pretty good agreement, and they have and the spectra collected are relatively flat. So that's good. We also took measurements on tissue simulating liquid phantoms. These phantoms comprised of polystyrene beads to provide optical scattering, as well as red food coloring for absorption. So we took measurements on 3 sets of phantoms. This first set, you can see here, this solid blue line is the phantom with just optical scatterers only, no absorption. And then this dashed line is the same phantom, but with this red food coloring added for absorption. So you can see that the diffuse reflectance decreases in the wavelength range that's consistent with the absorption spectrum of the absorber. So we did this in 3 sets of phantoms, each one with progressively lowered scattering coefficients. So you can see that this is kind of what this data looks like. And so we did this also in both probes. You can see that these spectra are pretty consistent between both probes, looking at both with the new components in our system. To characterize the fluorescence spectroscopy, we took measurements on a fluorescence reference slide using both probes. And with the similar exposure times for both measurements, you can see that the collective fluorescence spectra is in general agreement, and also in general agreement with what the published or the manufacturer fluorescence spectra should look like. We also took measurements to characterize the Raman performance on naphthalene, which is a well-known Raman standard. And you can see with both probes that we're able to collect spectra that look pretty similar. With the 4 distinct peaks of naphthalene show up in both probes. So these are encouraging results. In vivo, we also took measurements with all 3 forms of spectroscopy in human skin. And so these are the results from the current probe. You can see it in diffuse reflectance. There's the typical drop in diffuse reflectance around where the hemoglobin absorption band is in the 500 to 600 nanometer range. You can also see what the fluorescence and as well as Raman spectra look like for this probe. With our new probe, the shape of the spectra also look pretty consistent, pretty similar. And if you look at them side by side, you can get a better sense of how this looks. So I think we have some promising data that shows that the performance of these probes are pretty comparable. So kind of our conclusions from this study is we were able to characterize these new components for our new spectral biopsy system, including these new light sources and miniature form factor spectrometers. As part of these characterization studies, we compared the performance of these 2 probes that we have, and we showed that the new design looks to be promising. Some system improvements that we've made. The system is smaller, a little bit easier to move around the clinic, and the use of these OEM components should lead to a cost reduction of around 50% from the original system. And finally, we were also able to show that this simpler probe design looks very promising. So sort of to summarize everything between our current system and new system, as you can see, we've tried to replace the xenon flash lamp and nitrogen laser with the multi-wavelength LED light source. We've replaced the Raman light source with a higher power 830 nanometer laser, and also moved to these small form factor spectrometers for both diffuse reflectance, fluorescence, and Raman collection. So one trade-off that we may have to make, or will need to be made in choosing these new components, is a slightly longer integration time, which is mainly due to the longer integration required for fluorescence collection. However, I think we can mitigate this trade-off by the fact that the optics in the new system are completely fiber coupled, which is an important consideration for a system that's meant to be used in a clinical application. And so to kind of get a sense of how much the footprint of the system is improving, as you can kind of see with this old system. Here's a picture of the old system, and our new design is a little bit smaller, a little bit more clinical friendly. And hopefully looks very promising. So our future work in the study, we will take our new system into the clinic and begin a large clinical study of 250 patients to assess our approach in diagnosing skin cancer. And just as a plug for one of my fellow lab members, some other future work is to develop a biophysical model to analyze the data specifically from the Raman spectroscopy. So this is a presentation that she's giving later this afternoon if you're interested. So with that, I'd like to just acknowledge all the members of the Biophotonics Lab at the University of Texas and our funding sources, and I'll be happy to take any questions at this time. Thank you for your attention.